Hello everyone, and welcome to today's webinar on wireless current transformers. Before we get started, I want to go over just a few webinar logistics. Today's webinar is based on a full report by the National Renewable Energy Laboratory, and you can find the full report as well as a one-page infographic and four-page findings on gsa.gov, and that report's just been published today. Today's webinar will be recorded, and you can find a recording of the webinar as well as presentation slides also at gsa.gov, as well as all the previous webinars you'll find there on the Outbrief webinar page. Today's webinar is one in a series. We'll be taking a break in July and August, and in September we'll be hosting a webinar on smart motors. Smart motors provide real-time monitoring control by combining an innovative electric motor with a programmable variable speed drive. All GPG webinars offer continuing education credit through the American Institute of Architects. And to receive credit, complete the post-webinar survey. If you registered for the webinar, you should receive a survey shortly after today's webinar. If you don't receive that email with the survey link, please reach out to Michael Hobson. Today's webinar is set to listen only, but you can submit questions in the right side of your screen in the chat box, and you don't need to wait until the Q&A session at the end of the presentation to submit questions. In fact, we encourage you to submit questions well in advance of that. And with that, I'd like to introduce Mike Lowell, who was the GPG project manager and will be facilitating today's webinar. Thanks, Mike.
Thanks, Andrea. Next slide, please. Here we have the agenda for today. After I go over the agenda, we'll have Kevin Powell, Director of the Center for Emerging Building Technologies, give you kind of a 30,000-foot view of our program. Then we'll have Willie from NREL give us a presentation on the results of our report that's being highlighted today on wireless current transformers, the CT type of submetering. After that, we'll have Aaron Rodriguez, who's the building manager at the building location where we installed and tested this technology. And then we'll go back to Willie, and Willie will give you what we call a lay of the land presentation. This is looking at the broader smart metering or smart submetering technology because it's a quickly growing space, and it's got a number of different alternative ways of achieving submetering. And then lastly, we'll wrap up with a Q&A session. Next slide, and I'll turn it over to Kevin.
Thank you, Mike. And so, just a quick note about why we have an Emerging Building Technologies program at GSA. The big idea is that we want to know what next generation technologies are out there, how they perform in the real world operating environment of our buildings. And then based on those results, we feel that GSA can make sound investment decisions in those next generation technologies based on their actual performance. So that's the big idea of the program. In terms of submetering, this is, in some ways, I guess you could say, a holy grail, has been for the entire time that we've had the program. And the reason, of course, as most folks know, is the old truism that you can only manage what you can measure. So submetering allows us to get at that granular level, something down below that whole building meter. And what you see are the three key value propositions that we see as really being something that, again, a low-cost submeter could deliver. So billing, fault detection, and then the verification of energy conservation measures. So I got to tell you, I'm very excited about this webinar as well as the last one, this technology in general. And with that, I want to turn this over to Willie Bernal.
Great. By the way, this is Willy Bernal Heredia from the National Renewable Energy Laboratory. I'm a research engineer here, and I've been working alongside my team at NREL to deploy this technology and benchmark this emerging, I guess, submetering technology. So we were tasked with performing the measurement and verification for this technology. We can go to the next slide, please. Great. So let me just paint you a picture of what is happening or what was happening. So I'm trying to give you an idea of the incumbent technology. So we have two types for this. So what existed before, it was the advanced metering infrastructure. So you would mostly see this for whole building meters, for example, whether they were electrical, or water, or gas. And they were very limited to the amount of granular data that you can provide. Also, they tend to be very expensive. However, they give a very good two-way communication between the utility and the, I guess, and the tenant in this case, or the client, right? And on the other side, we had a more customized version of this, which tend to be very hard because it's really dependent on the building type. And every time we move to a new building, you have to redo the whole process again. So they tend to be very expensive on that side. It's very costly on a per point basis. They don't scale very easily, as you would imagine, in a large building. And usually what you would see a lot, there were some integration issues with the data, just because it wasn't, I guess, one solution to fit all needs. So if we can go to the next one. To the next slide, please. Oh, great. So now I guess we are moving to a new type of technologies. I mean, and I think technology is making this possible, and it's lowering the cost of introduction of these new emerging technologies. So we've decided to we split this into 4 categories. The first one would be a full panel meters, so they would monitor up to around 42 breakers in a single panel. They tend to use voltage step as well as current transformers, and they either work with revenue grade or standard current transformers. Then we have another category, which what we describe as wireless CTs. These are clip-on sensors, so they're actually a lot easier to install. However, they do require an electrician for the task, and they don't need a meter in this case. So they only use a CT, and they extrapolate power consumption out of an estimate of voltage. So they're not really trying to calculate voltage as the full panel meters. They're very good for fault detection. Lower power loads are problematic to track because they are self-power. They need some current through the wires that they're metering for them to work. The single circuit meter, that's another technology. This is for metering single 3-phase loads. It uses a voltage step. It's similar to full panel meters in that sense. However, as you can imagine, we need a meter for every single breaker, 3-phase load we have. So they wouldn't be an ideal scenario for fully monitoring a 42 breaker panel. They definitely provide high accuracy results. They come in revenue grade or standard accuracy. And the last one that tends to be a little bit more recent and is still in their development. It's what we describe as electromagnetic field sensors. These are stick-on sensors that go on the outside of the panel. There's no electrician required for this. They are very easy to install. However, they come at the price of accuracy. As they only measure electromagnetic, I guess, fields, there's a lot of interference between different breakers. So accuracy is not guaranteed by any means, though I would say they are definitely best suited for diagnostics and fault detection. Next slide, please. Great. So what this presentation is going to talk about mainly is the technology provided by Centrica. So originally we started the project with panoramic power. However, this company was acquired by Centrica in 2015. So we'll be referring to this type of technology from now on as Centrica. We deployed this technology at the Cesar Chavez Memorial Building. Also, we had laboratory experiments here done at NREL as well, and I'll describe those in a second. We can go to the next slide, please. Let me describe you the topology about this type of submetering technology. So as I mentioned before, they're clip-on sensors. So they're also very easy to install. Some of them don't even require tools for that. However, we have to open the panel, as I said, to actually get the cables connected to the breakers. As I mentioned before, there's no meters required. They are really gathering current information and not voltage. They're not measuring voltage in this case. But just to describe you how this works, so they are self-powered meters. They need some current going through the wire that they're metering to provide measurements. After that, they will wirelessly communicate with a bridge, which actually serves the purpose of long-term storage as well. And after that, these bridges can be connected to the cloud through either a cell modem or a Wi-Fi connection on site. After that, you will be able to see, I guess, data in real time through their web interface or their web services. Some of this technology also provides some data analytics for providing performance, I guess, performance reports on the loads for the building, for example. Next slide, please. So every type of measurement and verification experiment requires a very high accuracy and revenue grade meter in this case. We've had a lot of experience over the years with the Campbell Scientific meters. So they're high accuracy and they've provided great results in terms of data availability and also integration and installation issues. So what we did is, as you can see on the picture over there, you have the panel, and there's two types of lines going over there, the blue one and the red one. So the red one, it shows the voltage tab. So this type of meters are actually connected to the panel directly, so they're measuring voltage in real time, as well as current. So after that, they aggregate the current and the voltage and convert it into power. On the right side, those hexagons actually show you the meters in this case. As I said, they're aggregating the voltage and the current and providing power for the user and energy as well. So after that, they communicate through a protocol to the data logger that provides long-term storage. And finally, that gets communicated to a cell modem or a Wi-Fi connection, so they can be, I guess, they are available to the user on the other side. Next slide, please. So as I mentioned before, first we deploy the sensors at the laboratory here at NREL. So we decided to test them before taking them to the field. So we deploy them at a residential panel because of availability at the time. And we were measuring home appliances in this case. Let me point out that the technology is not specialized for this type of application, but it was a very good way to have a feeling and a sense of how the technology would perform. So we were measuring in this case, for example, the dryer and the electric range. Let me bring your attention to the legend for a second. So we have in blue the reference, and then we have two types of clasps, technologies. One is what we call the split and the standard. To give you an idea, these were two-phase loads. So whenever you see a standard, we were measuring both legs of that load, and we were adding them up. In the case of the split, we were simply measuring one leg, and then just doubling those numbers. So as you can imagine, the class standard version would actually perform slightly better, and that's what we saw. However, for both of them, as you can see on the graph, this is 15-minute data, aggregated data. And you can see that they're definitely successfully following the trend. They don't do that great sometimes in terms of actually following very closely the reference value. However, you can see when the device is on or off or when it's cycling as well. Next slide, please. This is a table actually showing the error measurements, just for you to have an idea. If you can focus on the right side of the table, you'll see the total energy error. So if you look at those numbers, you will see that these sensors tend to perform a lot better for consistent data, consistent loads, the ones that don't cycle that much. And in this case, for example, that would be the lighting O. That means that this is 120 volt lighting. And also like the refrigeration and dishwasher tend to be more constant loads. In the case of the washer and the dryer, the errors tend to be a lot bigger. And that's because there's a lot of cycling going around, for those two loads. And we actually hit the highest error measurement for the lighting at 240 volts. And that's because these are LED lighting, so you will see very small currents. And these sensors, as I mentioned before, they are self-powered. So they need to have some current going through the cable for them to work. So there's usually, if it's very low currents, they would be measuring 0, even though there's definitely some current going along the wire. Just to give you an idea when this technology, the way this technology behaves. So next slide, please. This is, as I said, these sensors are definitely designed to work on commercial panels, and that's what we wanted to test. So we went ahead and deployed them at the Cesar Chavez Memorial Building in Denver, Colorado. And we have two different types of load here. I just want to point out a couple of behavioral aspects of the technology. On the left side, you see north lighting. There's not, as you can see, there aren't really big swings on the power consumption, so that the technology was able to capture the load really well in the load profile, as you can see. And on the right side, there was a lot more cycling going on, and this was for the VAV system. Another thing to point out here is if you look at the right graph on the bottom, you see that sometimes the reference sensor doesn't go, the reference sensor is actually measuring some current and power. However, the clasp system is not, it's actually measuring 0. And that's what I was mentioning before, that these sensors require some current going through the wires for them to work. However, you can actually see that they tell you very clearly the type of behavior of the load, whether it's cycling or not. However, the accuracy of the sensors is I would say, is not ideal, but you will be able to identify a lot of, I guess, a lot of energy conservation measures, for example. You can definitely know whether the device is cycling or not, or whether it's on and off, or whether it's behaving in an abnormal fashion. Next slide, please. And here is a table for the devices that we were comparing. The first 4 are going to be VAV boxes, so they are heating and air conditioning systems. Then we have 3 lighting systems. And on the bottom 2 is the transformer, and I'll explain a little bit more on that. But if we focus, there's a lot of variability in the error, and this was energy error for each month. There's a lot of variability on the VAV, and that's because there's a lot of cycling, and the different months have different average temperatures. So you would see that they cycle a lot more, a lot less, and that actually affects the error that we get. As I said, sometimes they wouldn't measure correctly because they were drawing some current, but as it was below the threshold, it was actually recording 0. So that is one of the things that you can tell from the graph, from this table. In the case of lighting, it's a lot more consistent, as you would expect, because there's not such a large swings in power consumption, and they tend to be a lot steady. In the case of the transformer, you see there's actually two rows. One says panoramic pan 14 and pan 42. The one on the bottom is the one that actually uses voltage tabs. So in this case, there's a meter that is connected to a spur bracket on the panel, and it's aggregating the current and voltage to provide a better estimate of power. However, what happens here is that we didn't see much improvement from the standard pan 14, and the standard is the one that I've described before, is using just a wireless CT and no meter. There's no voltage tab for them. So you don't really have a measurement for voltage. It is just an estimated value at the beginning of the project, for example. And we didn't see much improvement on that. Next slide, please. And here I have a graph about energy versus power for the transformer. The transformer was interesting in the sense that the load was always above around 6 or 7 kilowatts. So there wasn't that much, there wasn't like large swings in the power profile. So the technology, the vendor technology did perform better. I think we recorded energy error of around 7%. However, here we're showing two things, the class standard technology and the one with voltage tab that we would expect it to increase the accuracy of the sensors because now we would actually have voltage measurements. But through the experiment, we deployed this voltage tab technology for 3 months, but we didn't see much of a difference. I think it was around 1% improvements. But here I just want to show you on the left side, for example, the energy consumption of the transformer. For the cases where, if you take a look at January, the power consumption, the error is actually much higher. There's a much bigger discrepancy between the reference and the class system. And we expected this because there was the wireless CT wherein, I guess, measuring large amounts of current in this case. So they were only recording small amounts of current, and that is definitely detrimental for the accuracy of the sensor. So if the wireless CT were to measure a much larger load, I think the performance of the system might improve on that. But if it's measuring very low currents, the accuracy of the system diminishes considerably. Next slide, please. Just a couple of words on the installation. It was a very easy installation because these are clip-on sensors and they do not require wires. So it creates a very clean, a very neat installation, as you can see on the right. So this is a panel at Cesar Chavez building. As you can see, we were only required to install the sensors. There's no cables running around, and that is great. It made installation really fast. We were able to install in 8 hours 144 individual CTs, distributing 13 panels, and 4 HVAC equipment disconnects, and including a couple of chillers. So as you can see, it's definitely a lot easier than the standard metering technology. And we were able to install this in both high and low voltage panels. The vendor provides software that streamlines the process really well. You're able to see in real time as you are connecting the meters, the sensors, in this case the wireless CTs. You can see real data and debug whether the CT is working or not. So that helped us debug any problems we had, and it made installation a lot easier. So next slide, please. So as part of the vendor services, they provide a report that shows, I guess, they provide a report with information on the loads that they are metering. So whether they're performing correctly, or what is the power consumption, or whether they're cycling too much or not. And through this type of reports, they were able to identify 7 energy consumption measures, energy conservation measures. So whether it was short cycling of AC loads, as you can see on the right side, you actually have the chiller that is cycling a lot, and also another AC equipment on the bottom right. They were also able to identify AC loads not correlated with outside temperature, as well as uncoordinated behavior between condensing and air handling unit equipment, permanent baseline consumption of both chillers, as you can see on the right. Through this type of, I guess, information, you would be able to schedule your chillers in a different way, so in order to save power. Also, they were able to see unnecessary HVAC operation during warm outdoor conditions, cycling of lighting loads during off hours, and that's pretty much what you see on the left, on the bottom left. This is a lighting system. It was actually turning on and off during the night, and as well as high energy consumption of lights during off hours. So all this type of ECMs they were able to identify, and they left that information for the building manager to act upon. Next slide, please. So we also calculated the payback for this type of technology. This analysis, it was a little bit limited in the sense that we were not able to act upon any of the ECMs that they provided. However, what we did is, I guess we work in some way, in a backwards way. So we calculated the equipment cost, installation, and the annual fees, and we added up all those costs and calculated what is the energy savings that we need to achieve through this technology to make a payback of 3.5 years. And what we discovered is that this is cost effective if we can save energy at a 1.3% level. And for this type of building is quite achievable, and also judging by the type of ECMs that the technology provides visibility to, so this is definitely a cost-effective way. I know the simple payback might not be the best analysis for this. However, you can see this shows you, that just gives you an estimate of how easy and cost-effective this technology actually is. Next slide, please. So some lessons learned and best practices. As I mentioned before, these CTs are self-powered, so they require some current going through the wire, and these tend to fluctuate, and at least on the specs of the manufacturer, they tend to be around 0.75 to 1 amp. However, we've noticed that they tend to be a little bit lower in the field. If this technology were to be used only as a sensor for collecting data and not so much providing the services of data analytics, I think it would be important for GSA to talk to the vendor to lower the annual subscription fees, because this might be a challenge for cost effectiveness, especially if integrating into GSA Link. Something important to point out is that we use the same backend as GSA Link, and we didn't integrate with GSA Link. It was not part of the project, but we use a very similar infrastructure, a very similar architecture in this case, that GSA Link. We were using SkySpark on the backend to aggregate all the data so we can perform some analysis on that. It is important to, when entering voltage and power factor assumptions, to enter the best estimate possible, because as I mentioned, the wireless CTs do not require a meter, and you don't have voltage information on that, so it would be better to get the best estimate of voltage at the time, whether your building is supplied with 285 as opposed to 280 volts. That would be a very important distinction, as it would drive accuracy higher. Another thing is it's important to have your panels properly labeled. I know because of retrofitting that it's a hard and challenging task, and sometimes tracing individual circuits is cost prohibitive. So it's important to have a good idea of what is the actual load consumption on that, either by measuring the spot right before installing the meter, just to be able to size the meters appropriately. There's a couple of different sizes for that. So if your load is only 20 amps, for example, it would be better to match that circuit with a smaller CT. And here it's very important to define the monitoring goals prior to deployment, so to save some costs of, as I mentioned before, tracing individual circuits. Next slide, please. And some deployment recommendations. I think we identified two best use cases for this. We agree that fault detection and diagnostics would be a great use case for this technology, and also to augmenting the capabilities of GSA Link. In this case, if some system is not already connected to the BAS system, for example, for some lighting equipment is not part of the BAS system, the wireless CT can actually monitor and provide information on that load. Next slide, please. And now let me introduce you to the former building manager for the Cesar Chavez Memorial Building, Aaron Rodriguez, that will give you his perspective on this.
Hello, this is Aaron Rodriguez. Currently I'm the recurring service program manager out of the Office of Facility Management here in GSA Region 8. Thanks, Willie, for the introduction. I really appreciate it in your portion of the presentation. Next slide, please. As Willie had stated earlier, he covered pretty much the installation and touched a little bit on some of the maintenance. It was pretty simple. It was kind of less than a day. The project team worked together really, really well as far as we had a pre-meeting to make sure we had a good plan in place. That way when we're out at the panels, we're able to go ahead and implement the installation in a very, very quick and simple manner. As Willie had stated earlier, it does require some electricians in case we had a couple of them to open up the panel. There was no need to de-energize, which was very beneficial because anytime you're touching anything within that panel, if it's connected to building or tenant, people had to have, they have some concerns, so we want to make sure that nothing is impacted. In this case, there was no impact with normal business, both facility-wise and tenant-specific equipment-wise. The maintenance, there's no maintenance. The sensors are a clip and go. They are self-powered. One's clamped on, they either work or they don't. In this case, all the sensors that we had, the CTs installed, they did work. Next slide, please. So some of the use cases, the primary use case and the primary goal of our project team and the pilot team for this Centrica CTs and low-cost submetering effort was accurate billing for our tenants. Now, that was more specific, it was more focused around tenant-specific equipment, computer room air conditioning units, encouraging better behaviors, raising thermostat set points on tenant-specific equipment as far as those crack units, monitoring some plug loads in lighting. Our hope was to encourage tenants to change behavior, to be fiduciaries of the government, and cognizant of energy usage and the reduction. Unfortunately, in this particular situation, this pilot, these low-cost submeters were not a viable solution just due to the accuracy. So what our team went ahead and did is we regrouped to modify the and determine and identify some realistic goals. And we found that the meters could be used more so, as Willie stated earlier, as fault detection and diagnostics for our facilities without GSA Link, or even if we're able to incorporate these into our GSA Link and tie in through the BAS. Even though the meters didn't have the accuracy we hoped for, if we were to incorporate that into GSA Link, it would allow facility managers to quickly identify and pinpoint equipment operating out of schedule, which we were able to do in this case. Next slide, please. some of the deployment hurdles were ongoing subscription costs, kind of Willie alluded to that earlier. We would have to, a way to kind of bring those down would let them know that we would incorporate these systems into the GSA link. That would be the hope in the Cesar Chavez Memorial Building if that was the direction we were going to go in an effort to get those. Otherwise, we'd have to figure out a method in a vehicle to where we could kind of go ahead and get funding for those subscriptions and pay for those on a monthly or annual basis. One of the other hurdles that could be a potential hurdle is the GSA IT security, and I saw some of the questions come through. Our project team, we did work with the IT and IT governance board in order to make sure that this pilot was streamlined. And the complexity of this will depend on where the submetering system's network-based components are hosted. If the solution is deployed with the same architecture as the pilot scenario, whereby it has absolutely no connection with the GSA network or devices that are connected to our networks and our systems, the data collected and transmitted, it's anonymous, then IT security review would be a little more streamlined in the installation. It could possibly get approval a little more easy through the IT governance board. However, if the solutions are to be hosted on the GSA network, as a lot of us are aware, it makes data available to existing systems like advanced metering, building automation, GSA Link, or Maximo or CMMS systems. They'll need to go through a full GSA IT security review and a remediation process for the installation. So it could be pretty intense, and in some cases, depending on how that goes, it adds those extra hurdles. The Green Proving Ground, on another note, the Green Proving Ground, in my opinion, is a great program as it allows GSA to test new innovative equipment and technologies within our facilities to determine if this equipment is a viable solution to assist ensuring our facilities are operating at optimal performance. It also allows GSA to partner with NREL and Centrica to help determine this as well. As Willie stated, we installed some NREL meters to determine accuracy of the Centrica meters. As I had said a little earlier, in this case, this pilot was not a feasible option for the Cesar E. Chavez Memorial Building. However, if other GPG pilot projects are viable solutions, the GPG program affords facility managers the opportunity to have options to go ahead and install these systems at a more permanent basis and take the steps to do so. Next slide, please. I would like to go ahead and turn the presentation back over to Willie at this time.
Great. Thanks, Aaron. So here we have a picture of the type of submeters. Can we go back a second? Great. So here is actually, the slide actually shows 4 different pictures. Let me just go over each of them very quickly. So these are 4 different types of technology. On the left side, we have the NREL technology, but this is a full panel metering system. So this technology has been optimized to measure the the voltage and energy consumption of a full panel, and it actually requires voltage steps as well. And the same thing, like it doesn't have wireless CT, they actually have wired CTs in this case. And on the right side, we have the wireless CT technology. This is the Centrica technology, and as you can see, you can definitely install a lot of wireless CTs on the panel, and they don't require any wires. And on that picture, you see that is the bridge over there that is collecting all the information from the CTs. A single bridge can actually take 250 can connect to 250 CTs. The next one, that is we have a project undergoing for that technology. This is the Miazon technology, and this is more as a single circuit meter. So it provides voltage and current measurements for each of them. However, you require installation of that for every single, you require 1 meter for every single three-phase point. And on the right side, we have a picture of the advanced metering infrastructure. As I said, this tends to be more for a whole, for metering the whole building power consumption, and they definitely provide they are very costly and expensive, and this is more like an incumbent piece of technology. So can we go to the next slide, please? So I wanted to, for this project, we want to analyze all these type of meters and try to get an idea of how they perform in a couple of categories. And what you see here is a table summarizing those, I guess, the qualities of this technology. On the top side, we actually are showing it actually shows the technology that I just described, going from the full panel meter to the wireless CTs to the single circuit. Also here we're including the electromagnetic field sensors, the one that I talked about at the beginning of the presentation, the one that are stick-ons, and the AMI technology. And we created this category that, let me just describe it in a little bit. So is the tenant equipment building, whether this provide high accuracy high enough so that they can be used for tenant building. There's also the fault detection and diagnostics category, so whether they can provide some insight of how the load is performing, as well as energy visibility and energy conservation measurements, capturing whether they can provide, I guess, a baseline and provide information on this type of savings that you would achieve, even that you implemented those ECMs. As you can see here, the wireless CTs, I guess we put them under the category of fault detection, diagnostics, and energy visibility. As I mentioned before, they successfully provided that type of services. They were able to identify 7 ECMs for a building. We didn't put them on the tenant equipment building because of the high error rates that we observed during the deployment. And we also wouldn't put it on the category of ECM capturing because for the same reason, because of the lower accuracy achieved. But here you just can give, you can see an idea of what this type of technology is capable of. In the case of the single circuit, we see that they are able to provide tenant equipment building because they provide high accuracy due to the voltage step in this case, and also the ECM capturing. However, for a large, I guess, a large installation, those are not suitable for that because they take a lot of space. They would be great for actually metering the mains of the panel, for example, or a couple of single loads or of large loads, but not to actually meter the whole panel. The same thing for the electromagnetic field sensors. They're great for fault detection and diagnostics and energy visibility. However, the error is unbounded in this case just because of the interference between, I guess, adjacent breakers. Whether you have a big load on one and a small one in the other one, there's no guarantee on the error. And AMI, they are great at providing high accuracy for the measurements. However, they're very expensive, and you cannot install them in your building for multiple loads. I think that would be very cost prohibitive. And what we also saw for the full panel meters, they tend to provide a little bit more flexibility for tenant building, fault detection diagnostics, energy visibility, and ECM capturing. And on the bottom here you see some estimates of the cost for this type of technologies. As I said, this cost is what we could obtain from the vendors. However, GSA being such a large client, I think there's, I think they would be able to sort out what type of services GSA might want, and I think this might be a conversation that GSA might want to have with the vendor, just to try to fit the needs of GSA in this case. And I think that's all I have for today, and we can jump into the Q&A.
Okay, thank you, Willie. Let me link up to the question sheet. Okay, can you hear me?
Yes, we can hear you.
Okay. So first question is from Keith. Can you talk about use case boundaries for this technology, i.e. what size and type of buildings is this technology used for? Can you think of any limitations, Willie, or?
Yeah, this is a great question. So I think there's no much limitations for this. I think it's more about designing prior to the deployment which type of loads are most important. In the case for fall detection and diagnostics, we're talking about the large loads like HVAC and chillers and that type of equipment. And I think that could be really narrowed down to that. I don't see there being a minimum and maximum size. However, due to the installation costs and all that, I wouldn't see this in a very small building. I think it would have to be for the Cesar Chavez building, that was a 10-story building, and I think it's like 180,000 feet squared. I think this was a great match for this type of technology. As you can see, there's a very cost-effective, and they can definitely provide. We believe that they can provide savings for what we saw on the table, that I think was 1.3% of energy savings, and that would make them cost-effective. So just to mention that, I think it's really the type of deployment that you're planning to do that. But if you just focus on large loads that tend to be the main culprits for energy consumption, I think that it's like mid-sized buildings. I think it's around that.
Thanks, Willie. And then I'm going to tackle, both Linda and John talked about the GSA IT environment. Frankly, anytime a technology is added to a GSA building, it has to go through a IT security assessment process. In the case of this technology, what I guess makes it stand apart from many technologies is it has no control functionality. It just provides data. And so in the case of our pilot, IT security did review the technology. They determined, again, it doesn't provide, number one, it didn't provide any control mechanism. And number two, in our pilot situation, it didn't connect to the GSA network. And so we were able to receive a waiver and proceed. If you were to deploy this in GSA buildings across the board, it would have to go through a more rigorous IT assessment process. If you mimicked the testbed location where you were just sending data to the cloud, I was told by IT security that would be a reasonably, as Aaron shared, a reasonably expedited IT security assessment. There'd probably be little, if any, remediation necessary. If you were to add the technology and have it connect to the GSA link through the network or connect to the BAS, of course, it would go through a more stringent IT security assessment and go through a remediation process. But given that, again, it's just data and it's not any it doesn't have a control function, I think it's very likely that it gets approved by IT security. On to Leslie. Leslie asks, do these submeters measure power factor and harmonics? And if so, how long would the measured data be stored? And Stephen Meyer, I guess, already answered in the chat that the PAN42 sensor, which has a voltage tap, monitors power factor and frequency, whereas the CTs do not. I went ahead and asked the question because I wanted people to know, but Willie answered it later. What is the rated minimum security, or the minimum rated current level for the CTs, and for them to be powered up and provide the necessary accuracy, you need 1/4 to 1 amp. Rod asked, well, what is CLASP? And CLASP is Circuit Level Analytics and Submetering Platform. And of course, in the case of this presentation, we are talking specifically about CTs. Juan brought up a point on one of the graphs, Willie. I can't recall which graph, but there was one graph where there was a relatively low transformer energy consumption for July, and he thought that might be an anomaly. I don't know if that's something you noticed and you can speak to it, or...
That's for July. Well, we definitely see that there's a drop in the energy consumption for the month. It's not that large as in January or February, but I think that's a very good question. We're pretty sure the reference sensors as well as the Centrica ones were recording similar measurements. So, and just let me say that this is for the transformer. It's not for the whole building. So there's a certain type of loads on here that might actually behave differently. I think the transformer had some HVAC equipment, but at the same time, it had other ones like lighting, I think, and some other type of load. So it was not the totality of the building. Whether that is an anomaly, we didn't see that as being. Oh wait, actually, let me rephrase that. I think I'm trying to remember that it's been a little bit of time, but I think that happened because we weren't collecting data for the whole month or something like that. I think there was some interruption in the data, and that might have been the problem in this case. I think that's the case. I'm not 100% sure. I know we at some points of time we had. I think it might have been either the reference sensors or I guess the vendor technology that was not collecting data at the time, so we couldn't aggregate the data for the whole month. I think as well. I think that might have been the case in this for that specific month. I can definitely get back to you with an answer because we definitely know that. It's just that I don't have it fresh in my mind.
Thanks, Willie. And one thing I'll share is that I know you're from Texas, and here in Colorado in the Rocky Mountain West, we see nighttime temperatures. Well, number one, we have a dry climate. We see nighttime temperatures, in the 40s and 50s. And so we utilize a lot of free cooling, flat plate heat exchangers and things like that. So we have other things at our disposal that you may not have in the hot and humid South. Rod asks, what does ECM stand for? And that's Energy Conservation Measure. And then Ed asks, how many of the ECMs could have been discovered by a traditional energy audit? Willie, I'll take that and you can chime in. I would imagine most of them could have been picked up by a traditional energy audit. That being said, we look at these submetering systems, low-cost submetering systems, as a low-cost alternative to a more robust energy audit. I don't know, Willie, if you would concur with that, but...
Yes, I think I agree with this. This is I guess a solution for I guess real-time data analytics. These type of reports, I think the vendor actually produces on a regular basis. You can also set alarms for them to tell you whether something is not operating properly, as opposed to wait for you to notice some problems. So actually conduct this type of energy audit. So there might be some differences there.
Right, thanks. And then Winston asked what software was used to accomplish the data analysis, and as Willie mentioned, they utilize SkySpark at NREL, and coincidentally GSA Link, which is our kind of fault detection system, also uses SkySpark. Keith asked, can you estimate how long the class sensors might last? Stephen, I don't know, Stephen from Centrica is on the line. I don't know, Stephen, if you would have an answer to that. And you may have to unmute pound 6.
Let's see. Good afternoon. This is Stephen.
Yes. Hi. Yes. We can hear you.
Yes. Hi. Good afternoon. This is Stephen Meyer from Centrica. I chiefly work with all our panoramic sensors. What was the question again?
Basically, how long do the sensors last? What's their lifespan?
Oh, I have not had that question asked before. I've been with this for 5 years now, installing, and I've had not. They last quite a while. I don't have an answer for that. It's quite a long time. If I knew exactly, I don't. There's not an expiration date that I'm aware of. Of course, there's updates and upgrades, but usually on a software level. Our sensors work. They're pretty robust.
Okay, great, thank you. And then Rod asks, what does CLES mean? And Willie, that's circuit level electrical submetering. And then Patrick asks, what's included in the annual fees? Steve, and are they assessed per site or per wireless CT? And Stephen, you could maybe speak to that as well.
I'm in the engineering aspect of it. This is more of a sales issue. I don't know if we have a salesperson involved in this. I cannot answer that. I don't know. I don't have the numbers on that.
And Willie, I think you had something on your graph. Wasn't it something like $15 per CT?
Yes, let me just quickly double check that. We're talking about the annual fees, right?
Right.
So, well, I guess I have two quantities. For the annual fees and the, let me think how many we had. I don't remember. But for what we would expect to install at a building like the Cesar Chavez building, you know, this 10-story building, we're talking about, the cost estimates were provided for that installation, and they were provided by Panoramic Power or Centrica. The annual fees we got were almost a little bit lower than $2,000 per year, like $1,926, and the equipment cost was $6,710 for that. So the total install cost per meter was around $64 per meter, but that's not including the annual fees. Hopefully that makes sense.
Okay, thanks. And that includes analytics as well, correct?
Correct.
Yeah. Okay, great. Thanks. Keith asks, can the class sensors be purchased without any subscribing to the vendor service plan? I don't know, Stephen. I know you said you're not sales. I don't know if you can answer that, but we can get an answer to that question later if Stephen doesn't know.
I don't know at this point. That would be a sales issue again. They're constantly changing things around.
Okay, let's see here. Let me cursor down. Ed asks, are the CTs powered indefinitely by energy harvesting, or is there a battery which is eventually drained? And the CTs are self-powered by the current within the wires. They don't require a battery. And as long as there's power in the wire, there's power to the CT. Keith asks, could these CTs be installed temporarily and then moved to another building? The answer is yes. And we actually had a discussion about that. I call it Ghostbusters. We had a discussion about that internally to our analysis team, and actually Centrica, we had a conference call with them and kind of posed that scenario to them. And the thinking is that you could do it, and it's kind of your call. But the thinking is that the installation cost is definitely something to consider. You know, if you're going to install it and then pull it out within, let's say, a month's time frame, over the life of those meters, that might get expensive, kind of a user's call. I think I will leave it at that. It's definitely a possibility, definitely a use case, if you will, that we discussed. And then Terry asks, would this benefit a data center? And then Stephen responded via the chat that it becomes a good diagnostic tool in data centers. And we actually, on a different project with a different submetering technology, did just that. We assessed a data center. It was very useful. And let's see, let's keep going down. And I think that's the last question. I'm going to turn it back over to Andrea.
Thanks, Mike, and thanks for all those great questions. So as we mentioned at the top of the presentation, you should all be receiving a survey. And if you want to receive continuing education credit, please complete the survey. If you don't receive a copy of the survey, please contact Michael Hobson. And with that, thank you all for being here, and we look forward to seeing you back in September for our webinar on smart motors. Thanks again.